So in this video, what we're going to do is start to unpack parts of Faraday's law. So I've written Faraday's law up here, and the part that we're going to deal with right now is what happens when we talk about a changing magnetic flux. What does the magnetic flux mean, and what do we mean by changing? So I know that earlier in the course what we talked about was this idea that there's a magnetic flux that has to be equal to 0. That is, that when you take a closed volume, so you take some closed shape like this, some three-dimensional shape, there is no net magnetic flux in any situation, right? We don't observe any net flux through a surface. And this actually led us to this idea that there can be no magnetic monopoles. That is, there are no sort of equivalents to electric charge in magnetism. There is no such thing as magnetic charge as far as we know. And so you might be wondering, well, why are we talking about changing magnetic flux if it's always 0? Well, there's a slight difference here in that what we're going to be talking about is the magnetic flux that is not the total magnetic flux through a closed surface, but rather through some 2D surface that is sort of a flat surface like a circle or something like a plane, something like that, as opposed to sort of a curved closed volume, okay? So in this case, what we're talking about is what we would call an open surface. So it doesn't enclose an entire volume, it just is some flat cut of space that we're looking at. So in that case, we can still define the magnetic flux as the magnetic field over some area. And so the way to think about that is to take some plane, some space, right, which has some area vector like we had when we were talking about Gauss's law. So it has some area vector that's perpendicular to the surface. And in this case, we're being very simplified. We're talking about a flat surface where the area vectors is the same everywhere. And you ask the question, well, how does the magnetic field point over that surface? And maybe it makes some angle theta with respect to that particular area vector. And so in that case, what we can do is say something about the total magnetic flux over that area as basically being the magnitude of this dot product. That is, the magnitude of B times the magnitude of the area times the cosine of the angle between the area vector and the magnetic field vector. Now, this is only true when you have every single magnetic field vector making the exact same angle with every single little area vector that goes across. If it doesn't, if you're on some curved surface or you have some complicated magnetic field, then you actually have to add up all the parts to figure that out. So we have to do an integral, just like we did with Gauss's law. So what we're going to say is the total magnetic flux, in general, is really the integral of the magnetic field over some dA, over some piece of area. So this will actually take care of sort of any kind of funky-looking, shape that has any kind of weird magnetic field pointing in any sort of weird direction, okay? Now, oftentimes what we're going to do is not have situations that are very complicated like this, but rather be able to use these sort of more straightforward situations. But this is in general how we'd actually define the magnetic flux. Now, when we're talking about how it changes, we have to ask changing with respect to what? And so in the case of Faraday's law, what we're interested in is how the magnetic field or the magnetic flux changes with respect to time. So if we go back to sort of our definition of magnetic flux, there's a couple of things that can change in this situation. So when we talk about the flux changing with respect to time, that actually means that the B field can change. That means that the area could change. You could have a loop or something that's changing its size. It's shrinking or it's so forth. So dA can change. And in fact, buried in here is an angle theta. That can change as well. So the orientation between the magnetic field and dA can change. So these kind of imply that you can change both the size of this and its direction, the size and the direction. And as a result, if you change those directions, you're actually changing these angles that the magnetic field and dA are sort of oriented around. So as a result, when we're looking at how this magnetic field, or magnetic flux rather, changes with time, those derivatives or those changes can be on any of these particular objects. Now, what we're typically going to have is a situation where we have a change that happens at some sort of constant rate. So in the situation where that is the case, we can actually take big macroscopic time steps and say, we can look at the change over some amount of time, delta t. And so we can figure out what the flux is at some final time. We can take the magnetic flux at some initial time, and we can divide that by the time change. So this situation would be if it's sort of a constant rate of change. And that'll be typically what we will have, is we'll have these constant rates of change. So in summary, what we're doing is we're unpacking what this idea of the flux is. So we've defined it in general, but we can understand, like we did with Gauss's law, that we're able to sort of make that quite simpler if the magnetic field is constant, the area is flat, and so forth. We also understand that the magnetic flux can change in a variety of ways. The magnitude of the magnetic field can change. The area can change. It could shrink or grow. Or the orientation between those two can change. So you can have a loop that sort of flips around, or a magnetic field that changes its direction. And what will be typical for us is that we'll take this sort of derivative definition and actually apply a sort of macroscopic step. So we'll be able to calculate what the magnetic flux is at some time and then what it is at some later time, because we're dealing with a constant rate of change.